So we saw in the last topic that we can make a standing wave if we overlap two travelling waves moving in opposite directions. And we also saw that one way that could happen is if a wave meets a boundary and bounces back. The incoming and reflected waves have the same properties but moving in opposite directions, and that's what you need to make a standing wave. Now we're going to look at the example of waves on a string that is stretched between two fixed supports at each end. This kind of string happens quite often in our everyday experience. For example, on a guitar, we have strings that are stretched and held fixed at each end. Or for example, in a piano, the same idea, a whole range of strings fixed at each end. Now a wave on this kind of string will meet one end, bounce back, and interfere with the incoming wave to make a standing wave. In fact, the reflected wave will also bounce off the other end, and we'll have waves moving backwards and forwards along the string, interfering, making a standing wave. The special property about this string fixed at each end is that the ends of the string cannot move. They're held down. That means that location has to be a node of the standing wave. Remember that a node is a part of the standing wave where there's no oscillation at all. And that limits what kinds of standing waves are possible on this kind of string. If you look now at the green wave moving up and down, you can see at the ends of the wave there's no motion at all. They're nodes. And this in fact is the simplest wave you can have on a string fixed at each end. There's a node at one end, a node at the other, and in the middle there's an antinode. If you look carefully, you can see for this particular wave that in fact the wavelength is going to be twice as long as the string. You can see there's only one half wavelength. If you look at that green curve there, it goes from a node up to an antinode and back down to a node. That's half a wavelength. Now, what's the next most complicated wave we could put onto that string? Let's change it to a different one where we have now two antinodes. Again, you can see that the string is fixed at each end, so there's a node at each end of the wave, and now I've got one extra node in the middle, with two antinodes in between those nodes. If you look carefully now, you can see that the length of the string exactly matches a wavelength of the wave. So on the same string, we can have a wavelength that's twice the length of the string, and now we've got a wavelength that's exactly the length of the string. In fact, those two wavelengths are half of each other, and so the frequencies will have the same relationship. The frequency of the wave you're looking at now is twice the frequency of the one we started with. We can keep doing this, adding in an extra half wavelength, an extra antinode, making sure we have a node at each end. Here's the next example. Now you can see we have a node at each end, and now two nodes along the wave. We call these multiples of wavelengths along there harmonics. The very first one we saw was the fundamental wave, or the first harmonic. This one we're looking at now is the third harmonic. And in fact, that number can often be easily remembered. It's the number of half wavelengths on the string. It's the same as the number of antinodes that are going up and down along the string. This one here has 3 times as many antinodes. It has 3 times the frequency of the fundamental. And just for fun, let's have a look at one more. This one here you can see now has 4 antinodes. The wavelength is getting shorter. The frequency is therefore getting higher. These are higher and higher pitched waves. What this tells us is that on any one stretched string, if you strike it, for example on a guitar with your finger or a plectrum, or on a piano if you hit the key and a little hammer strikes the string, a whole bunch of vibrations can be set up in the string, but the only ones that actually remain as standing waves are ones that are multiples of that harmonic. This in fact is what our ear responds to. We say that actually sounds like a pleasant tone. We're not just hearing a single note, we're actually hearing the interference of a whole range of notes, all harmonics, all which we think sound musically nice. Now let's consider another system where we might imagine reflection from the ends of our system providing us the conditions for a standing wave. What about air moving inside a column? Now this again has obvious musical instances, for example a clarinet or a saxophone or even a trumpet, where we have some closed container of air. Usually it's shut at one end by a mouthpiece or by the musician's mouth and open at the other end. So on a diagram here we can show a simple pipe here, closed at one end and open at the other. Remember, our sound is a longitudinal wave that will move along this pipe. Now the closed end of the pipe doesn't allow the air to move backwards and forwards like it would like to do in a normal compression wave. So in fact that means there's going to be a node at that end. So at the closed end just here, the air can't move, we will have to have there in our standing wave a node. It turns out that at the open end, the other end, the air is completely free to move, and that will always be an antinode. So at that end there, we will definitely have an antinode for our standing wave. So once again, what's the simplest kind of wave we can draw here that has an antinode at one end and a node at the other? We'll see here as we draw along, we simply go from the node to the antinode. If you look at that kind of standing wave, what's the length of the tube compared to the wavelength of that standing wave? Well, we haven't even got half a wavelength now, we've actually only got a quarter of a wavelength. So in fact, the wavelength of this particular wave will be 4 times as long as the column of air. Now we can do a similar thing as we did with the wave on a string and consider the next most complicated wave. Of course, it will have to have a node again at this end. It will have an antinode at the open end. But now we can fit one extra node in there. That will be the next most complicated way of making our standing wave. So when we draw that wave, we can see we go through node to antinode, node, that second node located right here, and the antinode at the open end again. So we've actually added an extra half wavelength again, putting that extra antinode in, the same as we did on the string, and now you can see we've actually got 1.5 waves in our standing wave here. Now, what these waves both on the string and in the column of air show is that these physical systems have natural wavelengths or natural frequencies that they would prefer to oscillate at. And indeed, that's again the importance in a musical instrument. You don't want to have to think about when I strike the string on a guitar or when I blow a note on my trumpet, what are all the possible waves I could make? There's only a limited number that will go on, the so-called natural modes that oscillate. And indeed, any sound that's near or close to that frequency will cause that to oscillate. If you sit a guitar in a room and you make some noise near the guitar, some of the strings will start to vibrate. They vibrate in what we call resonance with the sound around. In the next topic, we're going to be looking at the final aspect of sound we're going to consider, and that is the Doppler effect.